Will it stay or will it go? Merging LiDAR with geotechnics to characterize slope instability. We'll be talking a lot about the use of LiDAR or data derived from LiDAR to inform some of the things we do as geotechnical engineers or engineering geologists or geologists, and mainly applied to soil and rock moving downhill. A lot of this focuses on remote sensing. So many of you have probably heard this word. You know at least kind of what it is, but let's define it to get everybody on the same level. So remote sensing is the acquisition of information about something, a physical subject, a landslide, a rock slope, a building, without actually making physical contact. One particularly promising type of remote sensing for what we do is LiDAR, and it's been around, but its use is becoming more common. LiDAR provides us something special. It provides us spatial data, in fact, a three-dimensional point cloud that can be processed to do lots of different things, ranging from agriculture to engineering to evaluating disaster reconnaissance, all these things. So including mapping the ocean floor. Here's a map derived from bathymetric LiDAR. Geologic mapping and landform interpretation. Here in the northern, I shouldn't say Pacific Northwest, it is in the US, but basically Oregon, Washington, Vancouver, British Columbia, we have lots of trees, quite a bit, particularly in the western region. And while we can walk a landform and do some interpretation, it's hard to interpret what the ground actually looks like. LiDAR enables us to strip away trees and start to actually see what lies beneath. It even guides the operation of self-driving cars. In fact, some of the new iPhones even have a laser scanner. So LiDAR itself is alphabet soup. It's an acronym. It stands for Light Detection and Ranging Technology. And what it does is it's a laser. It shoots photons in a simple way, like at least a simple description here. It uses photons, knowing the speed of light, and can measure the time of flight of those photons and get a point in space, knowing the angle in which it's shot. It does that for millions of points per second, returning a point cloud. There's lots of platforms for it, everything from a satellite to a submarine to a tripod. And what it does for us in particular is it provides us a digital terrain model. And what we can do with that model is process away things like vegetation or other artifacts like noise and end up with a bare earth model of the ground that we can all of a sudden see lots of geologic features and past hazards and present hazards. So basically a DTM of bare terrain. How can we use this to benefit a lot of the things we do? Well, the list is too long for one slide, but I'll focus on a few things here. What we have is detailed topography. That's what we get from this. And that's useful for lots of things, including stability analyses, identifying unstable terrain, inventorying geohazards, for example, landslides. This has been a godsend for that. As well as if you have several data sets of LiDAR for the same place over time, you can measure change. Another nice thing is it's a spatial data set. You can integrate it with other sorts of geospatial information, highway networks, census data, whatever you have in space, and actually start to do some planning level exercises as well. Of course, you can derive things like slope, aspect, lots of features that are based on spatial data of this nature. Faults from past tectonic movements. I don't know if you've had a chance, but I'd encourage you to go to the Washington DNR's website. They have an art gallery with LiDAR, and some of it is absolutely beautiful. This is one of those images from a LiDAR DTM that shows a fault in northwestern Washington. Here is a hillshade of alluvial deposits, places that might be prone to liquefaction, paleochannels, things that you can't really perceive just walking the ground, but it becomes quite apparent when you use bare earth LiDAR. Of course, the deposits of past landslides, some of which are enormous, some of which we choose to build on. These are things that might not be so obvious using traditional surveying techniques. So to summarize why LiDAR is helpful to us, I will use what you've all seen from your slope stability professor. 3 lines. This is the slope you see on the whiteboard every time. And while it's intuitive, while it's instructive, it's not reality. Reality is more like this. There's the landslide scar, there's its outline, and the topography is much more complex. While two-dimensional analyses and simplified hill slopes are valuable and relevant, LiDAR allows us to get a little bit more complicated should we choose to. So we have this topographic data. We can interpret landforms, landslide features, scarps, deposits, whatever it might be. It allows us to take that topography and even use it for geotechnical analyses, including things like forensics. A back analysis of a landslide is particularly promising for that, and I'll talk about that applied at a large scale. Landslide susceptibility and risk. It's a geospatial data set. It's a map. A map is a universal language. What we can do is create maps injecting a bit of physics, a bit of slope stability, and start to evaluate and have indices for the relative risk or susceptibility of landsliding given a variety of conditions. And that's useful for planning. As well as looking kind of more into the earth sciences side, geomorphic relationships such as scaling laws between area and volume or magnitude and frequency. It allows us also, as I mentioned, to evaluate change over time if we're so lucky to have several data sets. A roadmap of today, what we hope to go through. One is some ongoing work where we are doing forensic analysis of landslide inventories mapped using LiDAR. We'll look at evaluation of regional scale, landslide susceptibility under a variety of antecedent moisture conditions, as well as looking at change, particularly in the most dynamic environment I can think of, the coast, where we have plenty of landslides and plenty of erosion. So with that, after that, we'll have some conclusions and of course, some time for questions. I'd love to hear from you. Let's get started. So LiDAR is pretty useful for back analyses and forensics for interpreting what's happened. You can map things like tension cracks and extension or compression ridges. It also gives us high resolution spatial data about scars or other features associated with landslides. So it's very applicable to singular events. Now, for a given landslide, you're often going to walk it around and map every feature you can. Springs, seeps, tension cracks, whatever you might find to kind of interpret the kinematics of movement. So for singular events, it's really, really helpful. But we can also use this data at a larger scale to get first order estimates of trends that we might observe about landsliding within different lithologies or different areas. So we choose to extrapolate it, at least as a test, to larger scale analyses. To do that, we introduce an approach to one, use those mapped features in the high resolution topography to infer rupture surface geometry, an estimate. Reconstruct pre-failure topography, basically fill in the hole, and then perform 3D back analyses on thousands of landslides, given assumptions, of course. And finally, infer some spatial trends relating to landslide morphology and its association with strength. So what do we usually do? Well, classical approaches, the tried and true approach is put on some boots, walk a cross section or a couple of them on a landslide. You might look for an area presumed to be the toe, a lot of compression or gouge. You might look for internal scarps and a head scarp and try to get an idea of the extents of the landslide. You might place some inclinometers, hopefully, to use conventional monitoring to establish where the rupture surface might be of a landslide. And you can use some of this information together to project a surface and get a best guess. Of course, there's the Cruden and Varnes approach, which is the oblate ellipsoid approach. And one of my favorite quotes is from a paper from Ulrich Hunger, where he said, "This type of failure is more common in textbooks than it is in reality, but it is an estimate, right?" And of course, there are landslide area volume scaling laws, such as those presented by Guzzetti et al. Or many other people. This has been done all over, including in Vancouver, BC. So these effectively relate area, landslide area, and landslide volume, and you can get a mean landslide thickness. All of these approaches have their application, their use. They have value, no question. But to perform inversions that are a little bit more generalizable for forensic analyses at large scales, we choose to just go a bit further and to use some of the topography we can glean from a LiDAR DTM to inform what that rupture surface might be. So what we do is we develop the spline method called the hybrid thin plate spline, where we leverage elements of most of these approaches, particularly the first and third one. But we use it for more generalized geometry, and we do it in 3 dimensions. So what this does is we take a headscarp. The headscarp is a daylighted failure surface. We use the landslide deposits as a boundary, particularly the outer part of the landslide deposits. And we use this technique to fit them with the projection of the headscarp and the surrounding terrain. The thin plate spline has utility for this because it's able to produce pretty complex shapes while maintaining curvature. So of course, you can kind of tweak it, turn the knobs to introduce what's called a regularization, or how much it adheres to these boundary or constraint points. But you know, we worked with several well-characterized landslides to try and tweak those parameters to see what works. So here, an example of 3 landslides. Inclinometers at shear depth are shown in red vertical lines. The inferred predicted landslide surface from rupture mapping is the red line, and the actual predicted surface is the black dashed line. So not too bad for an estimate, a first order estimate. We can use a similar procedure to reconstruct the geometry. Basically take all that rock, all that soil, and shove it back uphill where it came from. Now, you lose things, of course. You don't have the natural roughness of terrain and the likes of that, but it does enable us to try and start to say, okay, where did it come from? What was the source volume? And things like this. And it allows us to have an estimate of unfailed terrain. We use this technique on our landslide inventory here in the state of Oregon, mapped by Dogami. That's our geological survey, and they do a fantastic job of mapping landslides, particularly after we started mapping the state with LiDAR. So all of the landslides we use have been mapped using LiDAR, bare earth DTMs, and we can use the given polygons from this database, scarps, deposits, the likes, as well as the topography, to reconstruct those failure geometries and the source areas from each one. Start to look at trends and strength with geometry, mechanism, geologic unit. And in the end, we did this for about 8,000 landslides. It took a while. The computer was humming. What do we see? Well, as expected, there is a scaling relationship that is pretty well constrained between area and volume, and it follows a power law. Rock landslides and soil or debris landslides follow slightly different trends, but statistically insignificant. You might notice the coloring of all these points where we show area and volume for reconstructed topography. That coloring represents the mean hill slope angle on the surface for each of these. And you can see that it's somewhat sorted. Smaller area and volume landslides are kind of placed here, and they're steep, while bigger landslides tend to be more gentle. These magnitude frequency relationships also show that smaller landslides tend to be comprised of soil and debris, while larger landslides are of bedrock. But of course, this characteristic rollover that we see is often a sign of undermapping of small landslides, and I don't think this inventory I think this inventory has the same issue. So we have a rupture surface. We can reconstruct the terrain too. And I have the existing topography. Well, we can do a back analysis. So what we do is we take this 3-dimensional grid of the existing surface, as well as the rupture surface, and we can start to run a slope stability analysis. So what we do is we use a method of columns-based approach to back out what the strength might be. What we do is we use both the deposits and the reconstructed topography to do a back analysis for a given landslide. First, we take the existing deposits and the rupture surface and back out the friction angle. That's a mature slip surface. We assume that the bonds of cohesion, if you want to think of cohesion as a real thing, are gone. Then we take that friction angle, we apply it to our reconstructed landslide, and we try to back out what we call cohesive strength in this case, although of course in rock it's much more complicated. So we do this for all the landslides in our inventory for a variety of groundwater conditions, which of course is one of the biggest assumptions. As a geotechnical engineer and geologist, you know, there's so much uncertainty, but I really feel bad for our groundwater friends. They really deal with uncertainty. We did this with a hypothesis that somehow landslide size might be controlled or interrelated, at least, with strength on a large scale. So before we look at what we see, let's think about some basic precepts that you may or may not remember from slope stability analysis, from any course you took on it or from your experience. So some intuitive rules we have from those 3 single lines that we draw for a simple hill slope. And basic shear strength properties, well, we know soil, I wouldn't trust cohesion if you have it under long-term conditions, and it tends to be dominated by friction. There are things that look like cohesion, apparent cohesion, so partial saturation, roots, a variety of things, but generally more frictional, less cohesive. Under low confining pressures, friction can be amplified. So that's the role of dilation, particularly under low confining stress. Rock has friction when fractured, and the cohesion is a simplification of those stress-independent brittle strength, or tensile strength even, between rock bridges or intact rock mass. When we see something in a slope stability analysis governed by cohesion, generally, if cohesion is dominant, it's a deeper failure, and it accommodates sufficient shear stress to have a deeper failure. When it's governed by friction more so, they tend to be shallower, steeper failures. And of course, we know that increasing pore pressure reduces frictional resistance. So with this, let's plot an envelope of the entire Oregon Coast Range. Here's what we get from our landslide inventory and from our back analysis. And you can see, as any traditional stress space, there is effective normal stress on the x-axis, effective shear stress on the y. When we plot all the points and we do some fits, we see that the envelope is rather nonlinear. It's rather nonlinear, which is what we might see in soil or rock for that matter. So what we see here is that friction is high at low normal stresses, but tends to be suppressed at higher normal stresses. And there does tend to be somewhat of a trade-off between the magnitude of cohesion and friction with landslide thickness. And we kind of wonder why. We're still kind of asking the question, to be honest with you. But here we see the envelopes between effective stress and friction angle. Ignore the tail of this over here. There's no values there, but we can see that there is a distinct trend for friction angle with effective stress here. So this exchange in controlling strength is a little bit more apparent when you normalize the proportional cohesive and frictional strength. So here, these plots are busy, so pardon me, but the left plot represents landslide area. That's the x-axis for everything here. The right plot represents mean landslide thickness. That's the x-axis. So the blue shaded area represents proportional frictional resistance, while the red shaded area represents proportional cohesive resistance. And the bounding lines represent moving percentiles. What we see is with larger area, we see an exchange between cohesive strength and frictional strength to a level. And this likely owes to that brittle strength we might expect in rock. It's not pure cohesion, although that's a simplification, I admit. It's not purely that. The friction diminishes to some level in comparison to the cohesive or brittle strength. The same trends are generally observed for landslide thickness. And what we see, when we kind of look at the typical range where we might see weathered bedrock, say between soil and intact rock, well, we see that most of the exchange that we have occurs within this range. This is where we see, this is effectively a proxy for weathering. And that is where we expect high landslide frequency. So for shallow landslides, small failures, weathering tends to be the most aggressive here. It's at the surface, might be above the groundwater table, but it is the first thing to feel raindrops. So these materials are typically decomposed from native rock if they're weathered in place. And these failures tend to happen in steep, small, localized topography. They're depth limited as well by that interface with saprolite. These landslides are small and frequent. Soil on steep slopes doesn't stay in place long, but it forms quickly. Saprolite, somewhere between soil and rock. Now, I've found that that's a very dubious transition in many places here in the Oregon Coast Range in particular. Weathering's still pretty fast and it's in place. It might be partially decomposed depending on depth. And there starts to be a trace more of actual intact rock mass, so cohesion in quotes, as well as significant friction. Normal effective stresses are still low, but there still needs to be sufficient shear stress to cause failure in this range to overcome that brittle strength of rock when it's intact. These landslides are numerous on the landscape and reflect the rate of in-place weathering. And then there's the big monstrous landslides, bedrock landslides. The deeper you go, generally, the slower weathering tends to be. And weathering can come from lots of different sources, chemical weathering, tectonic weathering, lots of things. But generally, bedrock landslides are going to follow weaknesses, discontinuities. And at least here in the Oregon Coast Range, a lot of these big landslides tend to encompass gentle surrounding terrain. We see lower friction in this range, at least proportional to cohesive strength. And actually we see lower friction angles as well, depending on the assumptions of groundwater. Some reasons for this observation might be large normal stresses, suppressing any sort of dilation, polishing at the interface between fractures of rock. Could be higher pore pressures. It could be suffusion of clay minerals, which are known to have very low residual strengths. So, however, there is this increase in cohesion of intact rock, and that is probably, and to basically cause failure in this more gentle terrain, well, we need to have a sufficiently low friction angle and sufficiently high cohesion here. So we can take this data and start to do lots of things. For example, each landslide has its own native lithology. We can see here, and you don't need to look deeply here, it's a lot of stuff, but you can see that all of these little histograms here are slightly different. We can see that different lithologies have different mean thicknesses, different strengths, and all of that. Of course, subject to the bias of the mapper, but in the end, it does seem like some lithologies tend to be stronger than one another. And this is useful for planning, particularly at the desk when you don't have a lot of data. We can look at mechanism. This entire inventory was classified using the Varnes classification system, the classical one. And we can look at rotational landslides, translational landslides, rock, debris. And we can see that rotational landslides tend to have smaller friction angles, both for soil as well as bedrock. They also tend to be deeper than their translational counterparts, which have higher friction angles. This kind of thing can start to help us provide uncertainty or bounds or bookends on doing susceptibility and hazard analyses at a large scale. There's so much uncertainty, but it at least provides us with a bell curve. Great. So we can use this information for susceptibility, as I said, and we do. We take the same approach, same physics-based approach, method of columns that we use for back analysis, and we apply it as a forward analysis now, not an inversion anymore, but a prediction. And we use it for shallow landslides because, frankly, deep-seated landslides are hard to predict. But in the end, it's also a useful test. We use LiDAR-derived digital terrain models, our forensic inputs for strength, as well as remotely sensed soil moisture data from a satellite. And we develop a physics and process-based approach to look at a variety of disturbances, those being storm intensity, a 2-year storm, a 10-year storm, seismic forcing. We're all waiting on the big one. I suppose you are up north as well. And we have shake maps for predicted PGAs, or shaking intensity. And we can use that as an input for a physics-based analysis. And we can link this to practical spatial data. In this case, it was part of a project where you're looking at highway networks and potential impacts of storm events and earthquake events, and those impacts towards closure of highways and lifelines. One question we wanted to investigate was the role of antecedent moisture conditions on landslide. And by antecedent moisture conditions, I mean, what was the moisture in the ground prior to a disturbance? It changes throughout the year, as you all are aware, and we wanted to see how strong of a control is that on landsliding, at least as an intuitive exercise. We also wanted to look at the role of earthquake timing on landsliding. The susceptibility analysis takes the landscape, and it will take clusters of already unstable cells triggered by rainfall or earthquakes, and it will grow them. It will entrain material, necessary to achieve equilibrium, force equilibrium specifically, using the same approach we used before. We use the inputs of our strength distributions. We can use that for susceptibility and evaluating uncertainties. We use soil moisture data, SMAP, in fact, is the acronym, which is data from a NASA satellite, soil moisture active passive, which gives us volumetric water contents, both in the root zone, they call it, 1 meter in depth, and this is a model, but as well as at the surface. But we can use that along with some geotransfer functions to get a 0th order estimate of potential localized groundwater conditions or piezometric conditions, at least at a large scale, as an index. There are approaches to get an estimate of soil depth, although sometimes I think the boundary between soil and rock is rather gray. So here we use the Roaring 2006 hill slope model, where you'd expect deeper soils in valleys and convergent terrain, and more shallow soils at ridge lines. The spatial data we use for topography, again, is just a LiDAR DTM, 3-foot resolution, and our study site is well over 1,000 kilometers squared. We can use IDF data for storm intensity. That's all available to us in map form, which is another utility of using spatial data for these types of analyses. There's a lot of things you can compare. And finally, a shake map, as you can see here, for anything from a magnitude 8 to a magnitude 8.7 event. So we use soil depth and topography as boundary conditions effectively. And when we do this and we start looking at initial clusters, landslides start taking a natural discrete shape. It's not just a slope map anymore. There's specific pockets or hotspots where we see are less stable and they entrain material. Well, we can get an estimate of size, location, but what about uncertainty, the likelihood of landsliding? Now, you might recall we have distributions of strength. Well, that is our source of looking at susceptibility. So what we do is we might have a histogram of friction angles, let's say, and each one of these friction angles has an associated probability. Well, we can run our analysis for each bin of strength, with lots of failures happening for low friction angles and very few for high friction angles. And we can add up these maps where each cluster that's failed is assigned the probability of that bin. And when we add it up, we have a susceptibility map, which again shows at least the ranges of those discrete clusters and their likelihood of landsliding for the specific conditions imparted on the analysis. So to the questions we wanted to go to. Now, of course, a regional scale analysis is not going to be particularly accurate, but it does provide us an index, a comparison, intuition as to the role of certain events, at least in a simplistic fashion, a starting point. And with this, we wanted to ask some questions. For example, we've had some dry winters recently, at least down south here. And I've wondered, during a dry winter, how much bigger of a storm does it take to trigger the same amount of landslides as a smaller storm in a wet winter? How would landslide impacts be different in, say, deep in the winter in February versus the shoulder months of, say, April? These questions effectively revolve around evaluating antecedent moisture conditions. So for our given site, we take satellite-derived soil moisture conditions for each month, and we take the average for the past 5-10 years or so, and we can start to put bounds on what the observed moisture distribution is for the landscape. Of course, it varies depending where you are, but we can also get standard deviations for that, and we can see that there's strong seasonality associated with moisture content. We consider the mean moisture to be the average wetness of a winter, or a year for that matter. The +1 standard deviation is a wet winter, -1 a dry winter or a dry year. So this is busy, bear with me, I'll simplify it quite a bit. We ran this for every month for a series of different storms, and we've done that for wet, mean, and dry antecedent conditions. We have this coloring here, where white, pure white, represents some landslide area comparatively. we treat a 10-year storm during a mean year as the baseline condition to compare everything else against. It's arbitrary, but we just do it here. If it's red, there's more failure in terms of landslide area than the baseline condition. If it's blue, there's less. So as we see here distinctly, under dry antecedent conditions, well, most cases provide quite a bit less landsliding than the baseline case, with the exception maybe being a 100-year storm in January or February. If we look at wet conditions, we know that there's quite a bit of red. There's quite a bit more landslide area occurring, at least for this given threshold of susceptibility, when we look at this. And really, the only cases with less landsliding tend to be a 2-year storm or no storm at all. We can plot this as a time series as well. And you don't need to look at any specific line, but just consider the shape. The x-axis is the month, and the different colors represent different antecedent moisture conditions. So dry, mean, wet. There's strong seasonality associated with total failed area or landsliding, as we can see here. Of course, it depends on antecedent moisture, but it really depends on season. So we can start to look and compare. For example, a dry year, maybe a 100-year storm is approximately equivalent to a wet year with a 2-year storm. And of course, there are simplifications here that involve runoff and infiltration and the likes of that, but it's a starting point to evaluate, at least from a water balance perspective. We can look at the spatial distribution of landslides. The colored map here you see reflects the 24-hour rainfall for a given 10-year storm. We consider February antecedent conditions, and what we see is that landsliding is more concentrated in the west of our map, where there's higher moisture and frankly higher rainfall. You get a lot of rain in the Oregon Coast Range. Of course, there's expected more landslide density in steep terrain, although landslides happen in gentle terrain too. And there's a correlation between antecedent moisture and precipitation intensity. And we can look at landslide area density in terms of kilometers squared per kilometer squared, or in terms of slides per square kilometer. And we can see the trends are similar. From this approach, we can also, at least conceptually, start to develop a way to look at rainfall thresholds. Many of you may be familiar with rainfall thresholds, but if you're not, a rainfall threshold is usually an empirical procedure to say, for this given duration of rain and this given intensity of rain, will we expect landslides or not? And usually it's tailored to a site or a region or a catchment, but it's purely empirical. And to some level, it's tried and true. It's the basis for many early warning systems throughout the world. Well, one thing I always think about when I hear about that is that not every site is the same. And if you have a very large site, chances are rainfall thresholds are variable throughout there. So with this approach, at least we play around. We look at antecedent moisture, so dry, mean, wet, and we can run lots of different rainfall events, starting from a little piddly storm, the typical drizzle we see in the winter, up to a monstrous 100-year storm or higher. And with that, we can look at what clusters fail. When a cluster fails, finally, we've determined what rainfall is required to cause it to fail. And we can overlay these maps to start to develop spatial thresholds of what sort of rainfall is required for a given antecedent moisture condition to cause failure. So here, for example, you can see this color bar, 0 centimeters of rainfall to a monstrous cataclysmic 35 centimeters of rainfall in 24 hours. Under dry conditions, at least for this given susceptibility threshold, there's little pockets of yellow, but there's some blue and green areas where it might not take that much to kick off a landslide, but most of it's barren, most of it's stable under that range of conditions. Under mean conditions, we start to see a change, and particularly under wet conditions. Areas that were once yellow, high rainfall, start to turn green and blue, meaning that you need less rain to kick off landslides, and that the rainfall thresholds that we often consider, they vary based on topography, landform, strength, all these things. What about co-seismic landslides? This was actually the big question we're at least trying to probe. One thing I've always wondered is, what if Cascadia, the subduction zone event, happened in July versus February, I feel like there'd be very different outcomes. So what we tried to do is investigate this quantitatively, at least with the model we have, to gather an intuition of how different those cases might be. Well, again, the colors represent different antecedent moisture conditions ranging from wet and blue to dry and red. And the different line types represent earthquakes, but don't stress too much about looking at all the lines. Again, what we see when we look at antecedent moisture over a given water year is that there is strong seasonality in terms of landslide area for a given earthquake. If we have an earthquake in February, there's bound to be some more landslides than if we have one in May. So seasonality might result in up to 2, even 3 orders of magnitude change in landslide occurrence. Wet conditions result in about an order of magnitude change, and they might be overestimates. I wouldn't be surprised, but there is a difference. We can look at the same spatial distributions I described before. Naturally, we see more landsliding as we go west. We're closer to the fault, and of course, shaking will be more intense there. There's still notable landslide density in steep terrain, and we see a drop off as we go further east. We can use the same concept we used for rainfall thresholds to also develop maps, spatial analyses of yield acceleration. A yield acceleration might commonly be used for a sliding block analysis or to determine the seismic slope stability of a hill slope, whether engineered or natural. And usually it's considered a single hill slope scale. But I think we all would agree that it varies over a landscape. So again, what we do is for a variety of antecedent moisture conditions, we take a suite of PGA values, pseudostatic coefficients really, and we run each one to see what causes failure of a cluster. When failure finally occurs, we found the PGA that results in instability. And through this suite of analyses, we can start to develop maps of yield acceleration on a landscape scale, just as a first order estimate. We can see as we go from dry to wet conditions, well, we go from yellow, very unreasonably large accelerations, to start going more green and blue, more reasonable accelerations, at least for what's expected from the Cascadia subduction zone rupture. And we can compare them. Storms versus earthquakes. Sounds like the name of a Marvel movie or something, but we can compare the actual impact of these very different disturbances. We can see here solid lines, just they represent earthquakes and scale to the bottom axis. The dashed lines are rainfall, and you can see on the top x-axis. And then there's landslide area density. There's a crossover. We can see it, what the equivalent event would be. So for example, under wet conditions, half G would be about equivalent to 17 centimeters of rainfall in 24 hours. And we can look at this for a variety of conditions throughout. Generally, we see lower PGAs are equivalent to relatively large storms. And we know that the frequency of subduction zone rupture off of our coast here is about 300 to 500 years. That's recurrence interval. Large rainfall events, larger than the magnitudes you see here, have a recurrence interval of about 100 years. And one might infer, but not know, but infer, that rain events might be a stronger control in shallow landsliding, at least in the long term. I mean, practically geologic time. And that actually corroborates some studies that have shown that indeed, rainfall might be a bigger driver of landsliding in the Oregon Coast Range. So we can use this data. Eventually what we did use it for was to look at the impact of lifelines as a planning level tool. That's what it's meant for. It's not meant to be perfect, but planning level. And looking at lifelines that serve Oregon coastal communities. We don't have a lot of highways that get between the Coast Range and the populated Willamette Valley here in Oregon. So those roads are very important, both following an earthquake and after a big rain event. And we performed some simple risk assessments for those lifelines in terms of dollars and time. And we'll just look at one quick example and keep moving on. Here's our map of susceptibility for a given 8.7 earthquake, February antecedent conditions, no rainfall. Well, lots of susceptibility in the west. We can use a simple, very, very simple potential and kinetic energy based model to look at runout, basically Heim's law, to look at where that volume of a given landslide, which we can characterize for these clusters, we know their volumes, where it might go based on where it is. And we can look at the spatial correspondence or overlap with the highway system, in this case, Highway 6. If we have a volume that crosses the highway, we can start to estimate the volume that must be cleared, and we can sum it throughout the length of the highway here. So for this case, if you assume 1,000 cubic yards per day excavation rate, which is quite a lot, we'd have 94 days of closure. And we generated something like 100 maps of scenario-based analyses for a variety of corridors using this approach. So forensics and susceptibility are two peas in a pod. And really here we use LiDAR as kind of the foundational element to provide us the variability with topography, or the controls of topography associated with other spatial data sets. What it enables is first order characterization of landslide magnitudes and their morphologies, strength properties, at least a first order estimate, the relationships between strength and morphology, as well as evaluation of landslide hazard using other relevant remotely sensed geospatial data layers. It provides us a means of doing planning level evaluation of landslide impacts that is often of use to state agencies, and that's what it was in this case. They have to do a lot of planning for the case of an earthquake or rainfall in terms of stockpiling or planning for recovery. All of this has been facilitated by recent advances in remote sensing tools from satellites, from airplanes, and of course, injecting the most timeless thing, physics, something that we all work with on a daily basis. One thing I'll end on here, the last chapter of this, is that LiDAR is particularly useful for evaluating change. If you're lucky enough to have 2 digital terrain models for a given site, you can difference them, and you might see some very interesting things that would otherwise be imperceptible. Let's take a trip to the coast. Let's pretend it's sunny. Rarely is, but let's pretend. And let's talk about some of the landslides and coastal retreat and what that might look like in terms of change using some of this data that we've discussed and other data sets. Here on the Oregon coast, coastal erosion is a significant problem. About a third of our coastline is sea cliff of soft sedimentary rock, very weak, dubious to call it rock in some cases. Highway 101, well, it's a beautiful drive, mainly because it's very close to the edge of that sea cliff. You get great views of the ocean. I suppose most of the people in this room or in the Zoom room are probably looking at the cliff instead of the ocean, but it's a beautiful drive in rather hazardous and unstable terrain. And that is, it's near lots of sea cliffs that are actively failing, and it traverses dozens of very large, slow-moving landslides that march that highway towards the ocean. What we have is a project with the state, 7 years in total, and we're on year 6, that involves monitoring of 5 relatively active coastal landslides, about 7 kilometers of sea cliffs, and we're looking at impacts of erosion directly and indirectly affecting the highway network using in situ instrumentation, most of which has been sheared away at this point, terrestrial LiDAR, and in one specific event, UAS LiDAR. And what we've done is developed a few techniques to evaluate sea cliff failure and coastal retreat, as well as the role of those in landslide impacts on the highway. All right, let's get to it. This image shows one epoch, or 1 year, in this case, the epoch is 1 year, of change for a given sea cliff. This sea cliff is about a kilometer, about 500 meters long. And the color coding, red, as you might expect, represents quite a bit of change, 2 meters of change in the case of extreme red in a given season. If you go to green or blue, it represents accretion, or the buildup of material, perhaps from debris failing, perhaps from the advance of a landslide. Well, if we break down each one of these sections, what we see is that, particularly at the toe of these sea cliffs, the areas subject to the most wave contact hours during high tides and storms, there's pretty significant erosion. And this is what we would expect. The waves come up here and they scour away soft rock constantly. And that material is removed and leaves the sea cliff just a teeny bit steeper. Over time, that can result in larger failures. For example, you can see that there's quite a bit of change here, an overhang failure here, some cliff collapses here. It varies on the site, it varies on the year, it's incredibly variable, but we can measure it. This is that overhang, or this is that rock failure I was talking about, a collapse really. Here, the change specifically in this location is about 75 centimeters in a given season. And you can see little pockets of green up here where debris from an overhang failure has been placed. Here is a great example of that toe erosion we're talking about. And there's a beautiful gradient of the magnitude of erosion as we see. The lower down we go, the more wave contact hours. And we can see that for our sites. It's measurable. Over 3 years, we see that erosion starts to get pretty significant. And just a quick note, right here in that image, that map, the satellite imagery, there's Highway 101. There's how close it is to the sea cliff. We're not talking about large distances. ODOT, that's our State Department of Transportation, is rather concerned about some of these stretches and gathering easements in order to move the highway or to armor shorelines, which is not technically allowed at this moment. You have to get an exception. So in terms of the erosion, say for this section, we can see that there's a large slump that occurred over here as well, and that we can see little pockets that are variable for erosion rates in terms of meter of sea cliff face. This serves as an input for at least a simplified predictive model. We can take erosion rates and look at the depths or heights above mean sea level, for example, where they're occurring, and we can apply that to slope stability analyses and start to look at when we expect failure. We can derive the cross sections for those slope stability analyses from bare earth LiDAR. And we can look at the initial and evolving stability of sea cliffs and look at how they change over time. Do a retreat analysis. So we develop a very simplified model where we look at sea cliff failures, a variety of mechanisms really. And those 3 erosive mechanisms in particular are scour, wave scour, observed based on the observed and projected retreat data, considering total water levels, sea level rise projected, things like that. We can look at, and that's basically material removed from the toe of each sea cliff. We can look at overhang failures. Eventually, as these sea cliffs are oversteepened, you might expect a tensile failure occurring near the toe where there's an overhang. And finally, cliff collapse. So eventually the sea cliff is steepened enough to the point that it is just inherently unstable on its own and it fails in shear. So what we do is we create a model with a series of time steps. We start with an initial cross section derived from bare earth LiDAR, and we apply erosion where it should happen at the rate we've observed, or with tweaks for sea level rise, for example. And we watch the sea cliff geometry change with scour, overhang failures, and cliff collapse. And we can consider lots of things like self-armoring or groundwater change. And in the end, this is a simplified slope here, but you can see scour, overhang failures, and eventually you'll get a cliff collapse. And we can start to model this process. It will repeat again over time when the armor disappears, and we see that the erosion begins again with small overhang failures. We can apply this at a little bit of larger scale. This is for the site you saw before. You can see erosion occurring along the toe here and some full cliff collapses occurring as well. This was over an 80-year period projected for the given inputs, and we've run the variability is so large that you can get very different answers with different inputs here, but it's a start. We can see that there's a concentration of failures in the south, larger failures, and that some of the areas don't really have large failures, where the road actually crosses here. We can look at retreat over time at any arbitrary elevation. In this case, I'm looking at the approximate elevation of the sea cliff toe, about 7 meters above sea level. So the coloring represents red, which is now, and blue represents 2100, which is far enough away to not know how accurate our predictions of sea level rise or retreat would be, but it serves as an index for starting to characterize where we expect more retreat. So we can see that generally at the toe, it's pretty steady, mainly dominated by wave scour. However, there are stretches where there's big white jumps. Those represent larger failures, overhang failures, full cliff collapse. And we can see that it varies along the coastline itself, in some places affecting the highway, particularly here in the south. If we look at the crest of the sea cliff, the story is a little bit different, at least in the timescales we care about. We can see that generally the retreat is slow, but eventually sporadic. You might have large changes. And this owes to the necessity for a cliff collapse or a slump to occur to start to affect the highway network. So we can see that it's rather intermittent and sporadic, and it can't simply be evaluated through just taking an erosion rate and applying it over a while, over a distance. So that gives us an idea of sea cliff retreat from sea level rise, and just as a tool that our state is using. And we can use that changing geometry to determine retreat from lots of different lateral erosion processes. And we can look at the overlap with highway right-of-way and get time to impact. We can also use it to look at larger coastal landslide advance driven by the debuttressing of coastal erosion. So those rates we got from LiDAR, from modeling, from all of this, serve as an input if we'd like to look at the upslope influence of coastal erosion, the indirect influence of coastal erosion. Many of our landslides here in Oregon are driven by coastal erosion. The highway might be 100 meters away from the sea cliff, but erosion of that sea cliff causes the landslide to advance and the highway with it. So we use some of the same tools, our 3D rupture surface, 3D slope stability analysis, a finite difference solver using conservation of mass to look at movements and how the geometry evolves. And we use some of the data sets, erosion rates, for example, total water levels, to look at this. And it allows us to look at the sensitivity of landslide conditions to erosion forcing. The finite difference solver looks something like this. We might have some geometry, a landslide mass, and we can make it move. And it tends to follow rather intuitive changes in landslide geometry. And it allows us to look at, as it advances, subsidence at the head and accretion at the toe. I'll hurry up a little bit here, but what we do is we use those erosion rates, we can apply it as a mask here, and we can start to see what is the sensitivity of these coastal landslides to erosion. Here's an example. This is very aggressive erosion, the highest rate of erosion we've observed, applied over a 200-year span. You might note the retreat here, rather simplified, but here's the landslide, and you might notice it's advancing. Traversing the landslide is the highway, and you can see it being dislocated at the edges here. So despite the highway being quite far from the sea cliff itself, it still might be influenced by those erosion rates. We can develop simplified relationships here between, say, between landslide geometry, advance, and toe retreat. Generally, we'll see that retreat tends to exceed advance in most cases. That's not always the case when landslides are predominantly driven by groundwater, as some of our coastal landslides are. But under controlled conditions, erosion can indeed be a significant control on the advance of these coastal landslides. But not all landslides are driven by erosion. I'll end with a very quick snippet here about my favorite landslide in the state. It's got a name that's a little bit difficult to pronounce, Muscanaden, and it is probably the most active and destructive landslide on the Oregon coast. It's an earth flow, so slow-moving landslide, very large, seasonally active every year, and it's got about 20 million cubic meters in its volume here. On a good year, it'll move 2 meters. On a bad year, 5 meters. On a really bad year, one where we have a surge event, it might move up to 40 meters. In this case, that was February 2019, and that happened after pretty significant rainfall. This closed the highway for 2 weeks, and it was quite a sight to behold, the actual displacement of ground throughout the landslide mass. Here is a drone image of the most active zone, the transit zone of this earth flow, you see numerous tension cracks here, extension. And you can see ponds. This one's actually a pond for the local cows. And you can actually see seeps coming out of this landslide. There was a lot of rain. You can see the dislocated highway. There's an excavator for scale. This was a pretty significant event. And this picture was taken prior to the landslide slowing down. So they were trying to rebuild as fast as they could, kind of a futile effort. So here they are. There's another image. You see the tension cracks throughout here. So it was time to actually try and compare change for an event. What we did is we got UAS LiDAR, so taken from a drone, and we compared it to a previous aerial LiDAR data set to evaluate change. And what we used was manual feature tracking for features we could pick out throughout the landscape to start to see how much did it move and where, get an idea of kinematics. Here's what we see from change of two LiDAR data sets. Well, the coloring represents the magnitude of displacement laterally and vertically on the left and right respectively. We can see that the most movement, unfortunately, is concentrated right where the highway traverses. You can see the vectors of scaled movement and their directions as well. We note that it has typical earth flow topography. It's slow and then fast and then slow again, particularly here where it's more gentle in the lower portion. In the upper portion, we can see there's a gradient of velocity. It's slower upslope, and hence all the tension cracks in the extension. One of the most interesting things about this slide is that while we did see movements in this bench comprised of landslide debris, and a lot of the movement actually resulted in an entirely new sea cliff. Here's an example of that sea cliff right there. The original sea cliff from this point cloud is shown in kind of the brownish gray in the background. I was amazed when I saw that the actual landslide toe was somewhere underneath the tides at times. Here's the new sea cliff, which to some level is standing today, amazingly, since 2019. And you can see that it's heaved the gentle terrain through compression and heaved it up almost 7 meters in places. Quite amazing. And this is something we're able to measure through change analysis. With that said, I've gone a long time here. LiDAR is a tool. We have lots of tools, but tools are not always the solution. But they can be used with your brain or with your creativity to be a solution. Using engineering knowledge, using your interpretation of process is where we can really use things like this. I think that LiDAR is particularly useful for interpreting landslide processes and the topography associated with it, whether it's at a planning level or an individual landslide level. If we look at change, we can start to quantify things that are difficult to perceive visually. We can start to measure them and understand the controls on change, whether it be for a landslide or for erosion, whatever it might be. The regional scale assumptions we use are very coarse, of course they are, but they still provide an index or intuition as to how a landscape might respond to disturbance or how Earth's surface processes are controlled by the in situ conditions at hand. And there's always promise in injecting geotechnics and engineering geology towards larger scales, both as an inversion and prediction techniques. But of course, these techniques need to be used with interpretation and judgment and not used beyond that. Of course, there's a lot of people I'd like to acknowledge, a bunch of names you can see up here, but I'm very thankful to have worked with lots of kind, smart, hardworking people to come up with some of these ideas and come up with a lot more questions, frankly. At this point, I welcome any questions you might have, and I appreciate you sticking around even though it's a bit long.